Test. Hi guys. Let's begin. So welcome here to listen to my talk, or kind of a talk. So we will be doing a few examples for the OMK, and just for the introduction, I'm Tristan, and I have been a member for the Mathematical Olympiad team for Malaysia, and the OMK at the time when I was 18 was the selection test for the IMO. Well, now it's not already, it's the IMONs, but the OMK is still relevant because I think it's for other contests other than the IMO. Right. So today we're going to look at some how the maths in OMK or Olympiad in general are different from the maths you learn in school, and I will teach a few new topics that you might not have encountered. But I have to say right now that I'm also choosing in between going a little bit easy or harder, because if it's hard, most of you maybe can't follow, but if it's easy, maybe it won't be useful in the actual OMK. So I will be trying to be in between. So let's begin. Okay, just for you to have an expectation of what you will learn, I will go through a bit of logic and how proofs work in Olympiad or even mathematics in general when you go to undergraduate levels, because it will be vastly different from high school maths. And then we'll go through a bit of topics, and today I will focus on the two main topics, which is algebra and combinatorics. Okay, first of all, you have to know some basic logical notations. Like for every statement first of all is true or false, right? But given any statement, I can always negate a statement, right? Like, let's say I am a human, that's a statement. To flip it over, it's like saying I'm not a human. But of course, this is a case where you negate a true statement. But any statement can be negated. So for example here, X is a boy, then negative of X is not a boy. Now, the second statement here is quite interesting. All apples are red. So, what do you think the negation of that statement is? Some people might say all apples are not red because you just add a not inside the sentence, right? But can anyone tell me why that would not be the negation of the statement? Oh yeah, can't hear you from here anyway. So, well, all apples are not red. It's not a negation because, well, first of all, between a statement and its negation, one of them must be true. If your statement is all apples are red and your negation is all apples are not red, how about some apples are red and other apples are not red, right? That's an in-between situation which doesn't comply to both statements. So the negation of all apples are red, you can either write not all apples are red, that's the most direct way you can do it, just chunk the not at the beginning, or the more sophisticated one, at least one apple is not red. Is that okay? So first of all, let's see. This a statement here as an exercise. For all positive x, fx is greater than or equal to 1. Then to negate this, that would be what? So think for a moment. So here's a trick. There's something called for all, and there's something called there exists. So for all means everything, right? There exists means at least one of them is true. So first of all, when you see a for all thing, you can swap it to there exists. So for all positive x, fx is greater than or equal to 1. The negation of it, I can write it as there exists a positive x so that fx is less than 1. Is that okay? Because if all of the x satisfy this That means the negation will be there's at least one x that doesn't satisfy this, right? Okay, and then these two are quite simple. So the AND operation and OR operation. So if we say A and B, it's true if and only if both are true. And if I say A or B, it means either A is true, either B is true, or both. So I allow the possibility that both are true. Right? Okay, now this one's important because it will be quite important for our proving process later. So implication. So this is kind of what mathematics is all about. If a statement is true, what kind of other statement is also true? So A implies B. And well, like for example, this first example over here, x equals y implies x squared equals y squared. That's true, right? Because if two numbers are equal, you can apply any operation to them. But the converse, which is the other way around, is not true. If we start off with x squared equals y squared, does that necessarily mean x equals y? Not necessarily, right? Because you can have 1 squared equals negative 1 squared. And in that case, 1 is not equal to negative 1. Right? So implications might not be reversible. Alright. So later you'll see some false proofs that kind of makes use of this fallacy. And another one over here, down here, A is more than B implies A plus 1 is more than B plus 1. That one is reversible, right? Because I can subtract 1 from both sides and move in the other direction. So there are some implications that are reversible, there are some that are not. Okay, so far so good. Any problems so far? Okay, so now, since we said the possibility of the reverse of an implication being true, if A implies B and B also implies A, that means we say they are equivalent. And we like equivalent statements because no information is lost. So asking A is the same question as asking B, right? So I mean there's one example here. X is an equilateral triangle if and only if X is a triangle with angle 60 degrees only. These are doable in both directions, right? But just a few terminology. A implies B is also known as A is sufficient for B or B is necessary for A. But I don't really use that kind of that kind of terminology. But you will see some books use this terminology in case you ever encounter them. Okay, now this one's quite interesting. This is called a contrapositive property, and it says that A implies B is the same has the same meaning as not B implies not A. So I'll give you an example for this. Let's say we have an apple, right? Again, the apple example. So an apple is a fruit, right? So let's say A is apple, B is fruit. Apple implies fruit. But that means I can also say if something is not a fruit, it is not an apple. Does that make sense? Okay. So that's just basic logic. And now we're going to go into proofs. So proofs are quite different in Olympiad than high school, as I said just now. So first of all, we don't really use calculators for Olympiad. So you don't have to use a calculator for the day. It doesn't matter if you forget to bring one. And even if you encounter the situation where you need a calculator like 2019 times 2019, you don't really need to use a calculator. Even in a contest, if you want to write 2019 squared, they will still mark it correct because the point is the problem solving process. It's not about the computation. Okay, so the most common kind of proof is a direct proof. So for example, if the problem says given A prove B, then you just start with the hypothesis and then you try to imply the conclusion. So here's one example for the Bongsu in 2017, which is the year I took in 2017. So here's let ABC be a triangle. The altitudes from ABC are denoted HA, HB, HC. Prove that this inequality is true. So I'll let you guys think for a few minutes and see if you guys can think of anything out of this. So altitudes, I cannot draw here because So just to explain what an altitude is, if you have a triangle ABC, and let's say this is A, then this is what we call the altitude at A. So HA. And then you do the same for C, not this B. This HB, and this HC. So what does this look like? Something about A plus something about B is more than something about C. Does it look like some kind of inequality that you guys have encountered before? Like the triangle inequality is A plus B is more than C, right? But of course, A is not really 1 over HA, B is not really 1 over HB. But there is still some kind of resemblance, and maybe that actually helps to prove that. So, okay. Does anyone not know the triangle inequality here? So the sum of two sides would be greater than the third side. Because, well, the shortest distance between 2 points is a straight line, right? So if you go that way, then you add up, the distance must be more. Okay, so let's try, as we said just now, we want to try to relate A to 1 over HA, B to 1 over HB, or maybe just in general A are related to HA. So how? Is there anything in common that kind of connects these two concepts together? So the side and the altitude. Anyone? So what kind of concept of a triangle involves a side and its corresponding height? Someone was saying something. I think I heard the answer just now. Just not sure where it came from. Okay. So very deafening silence. So the thing that I'm thinking of is the area of the triangle, right? Because area is always base times height over 2. Yeah, so the side times the height divided by 2. I mean, you don't care about the divide by 2. And anyway, these two are related in terms of its area. So we can write A times the altitude at A over 2. I mean, the over 2 doesn't really matter. A times H over A equals B times H over B equals C times H over C, right? So at each side and its altitude should be in this inverse relationship. And so the original problem statement should be clearer now. Like, why does A become 1 over HA? Because those two are kind of like proportional, right? So, right. So let's see how we can write a formal proof. So a proof that I would write in the OMK context. So one way is to write it like that. I can first do some definitions that doesn't hurt. Like if you want to introduce some notations that would make your solution neater, you can. So I can denote lowercase a as BC and so on. So by the triangle inequality, if you have a well-known kind of theorem or fact, you can quote it and you don't have to prove it. But it's better to know why you know that's true, because that's quite important. So I can quote the triangle inequality here, and let's say the area is S, right? The area is S. So S equals H A times HA, B times HB, C times HC. I can substitute that into the triangle inequality. So lowercase a becomes 2s over HA plus 2s over HB, more than 2s over HC. And then you just cancel the 2s because 2s is obviously positive, right? So it's not 0, so you can cancel both sides without changing the sign of the inequality. And there's this black square on the lower right corner. This is well, it kind of means that your proof is complete. You can, well, it's optional to write. It just makes your solution neater, just to mark a point where your solution ends. It's not required, but it just makes it look nice. Makes it look nicer. So this is a classic case of direct proof, which is you start off with a few things that are true, and you slowly work your way out until the final thing that you want to prove, which is the last one. So as I said just now, A implies B does not imply B implies A, right? So you cannot start with the last statement. You cannot start with 1 over HA plus 1 over HB more than 1 over HC, and then work your way upwards, right? Because that isn't the flow that the question wants you to talk about. They want you to talk why, to discuss why the last one is true, not what if the last one is true, what happens. Is that okay? Does that make sense? Okay, but I said you cannot start from the last line. However, in some situations, you can, as long as you know what you're doing. So another way of writing this solution is to write it like that. It's kind of like the same concept but written differently. So I can start with the last statement, but it's not about saying the last statement is true or what. It's to write an equivalent statement to the first line up here. Because equivalence again can be used forwards and backwards, right? So if you want to work backwards, make sure that every step you do is reversible. So here I can write multiply both sides by 2 times the area. That's reversible, of course, because if you want to go backwards, you just divide by 2 times the area. And then you just say that's equal to A, the second term is equal to B, and the third term is equal to C. So the first line is equivalent to the last line, but the last line is true. So that means the first line is also true. So that's another way that you can write a proof. Because sometimes it's easier to work around information from the thing that you want to prove, right? You just have to make sure that you don't actually lose some information when you do this way. So for me, I would rather to write like that. But sometimes if you're out of time, you can start with the thing you want to prove and then just work backwards, making sure every step is an equivalent statement. Okay, so another one is called proof by contradiction, which I guess most of you have already seen for the proof of the irrationality of square root 2. But I won't be discussing that example, you can research it yourself. But I will look at a problem here that is from a book that at the end of the lecture I will recommend some books that you can see. So this is from Santos, page 9. Let a1 to an be an arbitrary permutation of 1 to n, where n is an odd number. And you want to prove that this product is even. So let's think about this. There are too many possibilities here, right? There are kind of like n factorial ways to kind of have a1 to an. You cannot really go for every case. Even if you want to go for every case, n is arbitrary. So n could be 1, could be 3, could be 5, could be 1001. So there's no way that you can cover every single case. So let's look at the final thing that we want to prove. We want to prove that this product is even. And this is a product of n numbers, right? a1 minus 1, a2 minus 2 until an minus n. What's an equivalent statement to this thing being even? Is it that all n numbers here is even? Or is it something else? Like if you have a bunch of numbers multiplied together to give you an even number, what can we say about that list of numbers? Divisible by 2. Not sure where that can. Divisible by 2, correct. So if it's divisible by 2, one of them must be divisible by 2, right? You cannot have everything odd, right? And in fact, that's an equivalent statement. You just need at least one of them being even. Then the whole product is even, right? So this final statement over here is equivalent to saying, well, at least one of them is even, like a1 minus 1 or a2 minus 2 until an minus n. So why does that help? So that's an equivalent statement that we can think of. But having the information that at least one of them is true, that's quite hard to prove, right? Like, at least one of them is true, which one? So what we can do is to assume that the result is false and see whether we get a contradiction. If we do, that means it cannot be false, right? That means it must be true, because a statement can only be true or false. And the negation of the statement, at least one of them is even, is that all of them are odd, right? So if the statement is false, If the statement is false, that means all n numbers over here, a1 minus 1, a2 minus 2 until an minus n, they must be all odd, right? If one of them is even, directly you have your result already. So let's say we are in the situation where all of them are odd and see whether we get something that's absurd, right? So here, what we do is we know that all of them are odd. And one thing that is nice about this problem is that a1 to an is a permutation of 1 to n, right? That means if I add everything together, if I add all n terms together, it must be 0 because a1 to an is just some rearrangement of 1 to n. Alright? So now, why is that a contradiction? And you might forget that n is an odd number over here. Some of you might have overlooked that. N is an odd number. We have n numbers that add up to 0, but all of them are odd. Is that possible? An odd number of odd numbers added up. Can that be 0? But 0 is even, right? So, like, odd plus odd plus odd, that's 3 odd, you must get an odd number. Odd plus odd plus odd plus odd plus odd, 5 odds, also an odd number. An odd number of odd numbers cannot add up to an even number, so that's a contradiction. And therefore, one of them must be even. And hence, the whole product is even. Any questions here? Okay. So, this one's another fun one. Again, it's from the paper I took, 27 Bongsu. Yeah, we'll move on to the Muda and Sulong one later, but we'll start with some easy examples. So, here, it's a very long question. An integer is called an autobiographical number if the first digit is equal to the number of digits 0, the second digit is equal to the number of digits 1, the third digit is equal to the number of digits 2, and so on. So, they gave two examples here, just to let you verify that you understand the question. I mean, it's quite redundant, but it's there for you to verify that you understand the question. Like 42101000. So the first number is 4. That means there should be 4 zeros in that number, which it does, right? There's 0 and 4 zeros at the back. The second number is 2. That means you should expect 2 ones in that number, yeah, which it also does. So you can kind of see what this means, right? Autobiographical number. So the question here is to find two autobiographical numbers with 4 digits and find one autobiographical number with 5 digits. So they don't want you to find like a 9-digit one like what they gave, but they want you to try the easier version of 4 digits and 5 digits. So there's no kind of fixed way to kind of tackle this problem, right? It looks like a problem of trial and error, which it is. You have to, if you take a piece of paper, then you can do some deductions like the first number cannot be 0, right? Because there's a 0 there already, and you cannot have 0 zeros. So the first number must be at least 1. So you do this kind of deduction process, so try and error process, and you can find some nice solutions. Like for example, okay, if you try it enough, but we don't have much time here, so I'm just gonna tell you what the thought process is. If you try it enough time, you can find two examples, 1210 and 2020. And for the 5-digit, you can also find 21200. But for Olympiad, it's all about proofs, right? You want to prove that your result is true. However, is it really necessary that we have to write down how we got to 1210 and 2020? Because if I write down 1210 and 2020 for someone, they can just verify that they are autobiographical numbers, right? You just type 1210, 10 correct, 2 ones correct, 1 2 correct, 0 3s correct. So it's verifiable, it's a autobiographical number, right? And the thing is, if it's verifiable, you don't have to say how you got it, because it's true. It's just an autobiographical number. The thing about logic or writing proofs is that you just want to explain why something is true. You don't have to say how you got 1210 or 2020. But this is also because the question said find two autobiographical numbers. It doesn't say find all autobiographical numbers with 4 digits. If it did say find all autobiographical numbers with 4 digits, then you have to explain why the two numbers you gave are the only ones. But since you already found two, you can just write it down. You don't have to explain how you got it. You don't have to write down your error, trial and error list. You don't have to. You just have to explain why these two are autobiographical numbers. But this is self-evident and it's easily checkable. So the solution you can just put like that: 1210, comma 2020, and for B 2120. You don't have to write any proof. But if the question says find all, then you have to write why they are the only ones. Does that make sense? So you might spend like a long time to find those numbers, but your solution can be just a very short one. So sometimes it's like that. You can have very short solutions, but very hard to think of kind of solutions. Okay, so this one again is for this problem. I'm not sure where, but about like last year. So this is another kind of proof by constructing a number, and here it says what is the maximum number of trailing fours a perfect square can have. Like 64 is a perfect square, it has one trailing four. And any other perfect squares that has more than one trailing fours? 144, yeah, so that's 12 squared, right? So you can find a few examples with trailing fours like 64, 144, but when it comes to three fours, that's probably where you can get stuck. It's quite hard to find one with three fours, right? However, if you've learned some kind of modular arithmetic, which I haven't taught here, but if you do know some modular arithmetic, this is the same thing as solving x squared is congruent to 444 mod 1000. And you can solve you can solve it by some very long process and get that one possible case is 38 squared. It's apparently 1444. But does it matter that you write why 38 is the solution? Because 38 times 38 is quite easy to compute, right? Just multiplying two numbers. But how you got 38 doesn't really matter because now you prove that there can be three trailing fours. Because it just say consider the number 38 squared. Yes, 1444. So that means you can have at least three trailing fours. But the question was like, what's the maximum, right? So 3 works, and apparently 4 fours cannot happen. Like ending with 4444 cannot. And that one, sometimes proving something doesn't exist is quite hard. And so therefore you also have to prove it. But in that case, it's not about proof by construction anymore. That's more like a, again, number theory problem. But if you understand this, then it's great. So the point here I'm trying to make is that 38 squared, you don't have to really explain how you got 38 squared. But when I did this problem, it took me quite long to find 38. So here, so I will write the answer is 3. This is also a very nice practice. We like to write the answer at the beginning, just to kind of tell the examiner, okay, I got the answer. But it just looks neat. So you write the answer and then you prove why it's 3. So 38 squared is 1444. That's enough to say that 3 is the maximum. I mean, like, the maximum is at least 3. Then you have to still prove that 4 cannot, right? Because maybe there is an example with 4 fours. So you have to prove that 3 fours can and 4 fours cannot. So there's two parts of this proof. So the second part here is to do some sort of number theoretic argument here. So the vertical line here means divide. That means the one on the right side is a multiple of the one on the left side. So here is like solving x squared minus 4444 is a multiple of 10,000. 4 is a multiple of 10,000. Then let's see what happens. We can deduce a lot of things from here. We can deduce that this number on the right is a multiple of 16, is a multiple of 5 to the power 4. But apparently, I think, okay, first of all, x must be even, right? Because x squared minus 4444 is an even number, multiple of 10,000. So x must be even, so x equals 2k, right? So whenever you have information, just use it. It doesn't matter if you think that it's gonna help in your solution. But just okay, if it's found that it's even, just substitute 2k to it. Then you can simplify this relation, right? So now it's 4k squared minus 4444. I can divide by 4. That will mean 2500 divides k squared minus 1111. Right? So to prove that this is impossible, what I will do is to say that now the one on the right is a multiple of 4, because 2500 is indeed a multiple of 4, right? So I mean, I know we're losing a lot of information here, but what I'm trying to do is to prove that it's impossible, right? I don't have to use the whole information. I can just extract some information from it and then say afterwards it's a contradiction. So here, if 4 divides this, well, 1111, this is a multiple of 4 plus 3, right? Divided by 4, remainder is 3, right? I mean, just look at the last 2 digits. So, yeah, it remains remainder 3. That means k squared minus 3 is also a multiple of 4. But some of you that have learned a bit of primary Olympiad will know that that cannot be true. A perfect square can only be a 4k number or a 4k plus 1 number. It cannot be a 4k plus 3 number. Okay, so you can prove that. You can prove that as well. And come back to here. So you can prove it by saying, okay, an even number squared must be 4 capital N squared. That's a multiple of 4. An odd number squared must be 4 capital N squared plus 4 capital N plus 1. So it's a multiple of 4 plus 1. There is no situation where its perfect square is 3 more than a multiple of 4. So that's how you can prove this question. It's quite a hard one, but if you know a bit of modular arithmetic, which I will probably teach tomorrow, then it can be. I mean, the part where you prove 4 fours cannot, it's quite okay. But the part where you want to prove 3 fours can, you have to spend some time to find that 38 squared. Any questions here? Ah. Yep. Okay, good question. So we proved that 4 fours cannot, right? But that doesn't guarantee that 3 fours. Ah, I see. Okay, okay, I know what you're saying. So you do the same process with this, right? Like 10. In that case, it will be 1000 dividing x squared minus 4. Is that what you're saying? Yeah. So let's see. So x squared. In fact, I can just look at this and try to modify this to the 4. So for the 3 fours part, maybe I can change this to 1000. Change this to 4. Yeah. So first of all, x must be even. That's fine. I divide by 4. I get this. So now it's like 250, right? So yeah. So I mean, this is equivalent to this. So to prove that 3 fours can, yeah, you're right. So you can prove that this is possible. However, I think this thing being divisible by 250 is a different condition from this, and it's kind of like you need. Probably shouldn't delete this. You need two statements, both to be true in order for this to be true, which is 2 divides this. Oh, that one can be easily solvable, and another one is 5 cube divides this. Right? Yeah, then this part is the hard one. Yeah, that's why I use that one. You basically reduce it to that, and then you find some k that works. So apparently 38 would work. So you can explain why that is true. Then if you do that, it's also a valid way of saying 3 fours is possible. But of course, once you do that, you will automatically get like an answer 38. So it's shorter to just write 38 squared works. Yeah. Okay. Okay. Great. So yep. So this one's called proof by induction. Um, anyone here hasn't heard of this from A levels or whatever? Oh, okay. Because you will learn induction for, I think, for the math or something. I'm not sure. So induction, you don't have to look at this bracket. This is quite a technical kind of statement. the idea of induction is that you want to prove something is true for all positive integers. So you have two ingredients to prove that. First of all is to prove that the first number is true, and the second ingredient is that if k is true, then k plus 1 is true. So if you have both ingredients, that means all of them are true, right? Because one true implies two true implies three true, three true implies four true. It's like a row of dominoes. So you design dominoes in such a way that every falling of a domino causes the next domino to fall. That's one ingredient. The second ingredient is you push the first domino. That's the second ingredient. So both of these ingredients will prove that it's true for all positive integers. And so this is from 2017 Sulong. So here they say given a positive integer n, that means you want to prove in general for all n. Consider all subsets of 1 to n except the empty set. So not all non-empty subsets. There would be 2 to the power of n minus 1 of them. Right? So for each subset, I consider 1 divided by the product of all elements in that subset. And then you kind of add the reciprocals all together. So again, sometimes if the question is very long, they can give you some examples to elaborate what they really mean. But again, the examples are just them being kind to you to kind of see if you can understand the question properly. So technically speaking, if they don't put an example, it's still a valid question. So example for n equals 3, the non-empty subsets of 1, 2, 3, these possibilities, right? 1, 2, 3, 4, 7 of them. Well, makes sense because it's 2 minus 1. So therefore, 1 over 1 plus 1 over 2, 1 over 3, 1 over 1 times 2, 1 over 1 times 3, 1 over 2 times 3, 1 over 1 times 2 times 3, all added together. I mean, here it's just a bunch of fractions. If you add them together, you'll get 3. Right? So the statement is not just S3 equals 3, but rather if you start off with n, the answer is always n. So as you see, it's true for 3. But of course, true for 3 doesn't tell you anything. True for 3 doesn't tell you it's true for 4, doesn't tell you it's true for 10, doesn't tell you it's true for 1000. So you want to prove true for all positive integers n, right? So if you notice a statement where it's something that you can, let's say you want to go from 3 to 4, right? You want to go from 3 to 4. Well, if you go from 3 to 4, your set 1, 2, 3 becomes your set 1, 2, 3, 4, right? But like for example S4, it will also contain all of these elements in S3, right? 1 over 1, 1 over 2, 1 over 1 times 2 times 3. These are all available in S4 as well. It's just that S4 has a few extra terms, those that involve 4. So whenever you have a situation where the next case kind of is connected with your previous case, you can do induction. Because you can try to see whether you can write S4 in terms of S3 and S10 in terms of S9 and so on. So in general, SK in terms of SK minus 1. So let's see. So one proof is to do induction. So I'll introduce some neat notation. This is the notation that I like to use. Square brackets n is 1 to n. So for the base case, n equals 1 is true. Just 1 over 1 equals 1. S1 equals 1. So now you want to prove the inductive statement. So you assume it's true for k minus 1. And then you prove that for k it's also true. Right? Any problem here? So, okay. And the nice thing about assuming k minus 1 is true is that you can freely use that information. It's already true because you assume it's true. Right? So, if it's true, this is a very complicated notation. But let's see if you can understand this. So, here, I start out with SK. I write out the definition of SK. So what's the definition of SK? It's to sum up. So to sum up 1 over capital pi A. Capital pi means like product. So capital pi A means like the product of all elements in that set. I mean you can write 1 over literally writing product of all elements in A, but that will be very long and probably can't squeeze it here. So I'll just write it 1 over pi A. Technically speaking, you should define pi A means what, but I forgot to write that. Okay, but pi A, what's A? Summing over what? I should sum over all possible A's being a non-empty subset of 1 to k. Right? So for the sum notation, you don't have to always write I equals 1 to n. That's what you normally use in college maths. So like you also can write statements underneath the sum symbol. So this just means you're summing up all of these cases where A is not the empty set, it's a subset of 1 to k. Is that okay? So, well, let's see. If I want to go from S3 to S4, for example, you want to go from S3 to S4, it's a bit wobbly my screen. S3 is 1 over 1 plus 1 over 2 plus 1 over 3, and then 1 over 1 times 2, 1 over 2 times 3, 1 over 1 times 3, and then 1 over 1 times 2 times 3. So this is S3. Can you write S4? Like something in terms of S3? Well, first of all, again, as I just said, all of this must already be here, because those denominators are also subsets of 1 to 4. But what are the remaining ones? The remaining ones are just those that have 4, right? Like 1 over 4, 1 over 1 times 4, so on. In fact, if I factor out the 1 over 4, what's left is just kind of the one on top, right? So 1 over 4, what's left is just 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 1 times 2. Because this will correspond to the 1 and 4 set. This will correspond to the 2 and 4 set. This will correspond to the 1, 2, and 4 set. Right? So whatever's in this bracket is just this again, except one term. Which term? Just the set 4 itself, right? So there should be one more. Because if I factor out, this is like an empty set. But we don't count the empty set in S3, right? So like the term that corresponds to just 4. If I factor out the 4, it's the empty set. So just add one more 1 over 4 at the end. Is that okay? So basically, conclusion, S4 is just S3 plus 1 over 4 S3 plus 1 over 4. Right? So of course this is just a 4 and 3 argument, but you can easily generalize this to k and k minus 1. Right? So what we do here is okay. So I split this term into what I did just now. Except just now is for 4, now it's just for k. The first term is the same sum, but with subsets of k minus 1, 1 to k minus 1. The second one is the same one, but multiplied by k, and then there's an extra 1 over k at the end. So same thing as the S4 case, I just generalize it. So I just substitute it in, because I know that sk minus 1 is k minus 1. That's true. So we can plug it in, so it becomes k minus 1 plus 1 over k times k minus 1 plus 1 over k. And you rearrange that, you get k, which is nice, which is what you want. So you basically prove that if the case for k minus 1 is true, then the case for k is also true. So that ends the induction. Again, that you can write your induction proof however you like, as long as your idea is there. Is that the first one is true, the following ones are also true. Is that okay? Any questions? Oh, this is another solution which is a short one, but again, it's quite hard to think of. In fact, now this is kind of like something out of the blue. Suddenly, so this solution, it doesn't use induction, but the first sentence is consider this expression over here: 1 plus 1 over 1, 1 plus 1 over 2, and so on. Multiply up to 1 plus 1 over n. It's quite weird, but it doesn't matter. It doesn't hurt the truthness of the proof. I can consider such a thing. The fact is, if I expand this product out, like what happens when you expand? You choose one element in the first bracket times a second. You choose one element in the first bracket times an element in the second bracket, and so on and so on. In fact, if you write out everything, it kind of expands to become 1 plus Sn. Anyone see how that works? Like, if I try for S3, for example, so S3 would be 1 plus 1 over 1, 1 plus 1 over 2, 1 plus 1 over 3. Let's see if it really is 1 plus S3. So you can have 1, 1, 1, so that's 1. You can have 1, 1, 1 over 3. That's 1 over 3. You can have 1, 1 over 2, 1. That's 1 over 2. You can have 1 over 1, 1, 1. 1. And you get 1, 1 over 2, 1 over 3. That would be 1 times 2. 1 over 2 times 3. So you can kind of see that it expands out completely into what we want. But except there's an extra 1 over here. So this is kind of like what we call a more ingenious proof, because it's actually something you can explain in short terms, but it's quite hard to think of. So in fact now we just found out that this is 1 plus Sn. You can just say Sn is just this thing minus 1. But those fractions is just like a telescopic product. The numerator of the first term cancels with the denominator of the second term. So you can get n. Any questions for this proof? So this is not induction, but I just want to show that there are always many ways to approach a problem. Is that okay? Okay, so that's the type of proof. Again, type of proof is kind of a vague term. The 4 types that I just said just now are just like a very vague list. You can prove however you like as long as the logic of your proof is true. But now I'm going to talk about some few common techniques that you can use in a proof that you might not know existed before. Now the first one is really quite weird. So in high school, in college, you're not really supposed to guess an answer for a question, right? It just doesn't make sense. They always want you to write a working and solve the solution at the end. But for this kind of higher level or more advanced kind of mathematics, you can guess an answer, but provided that you prove why that is your answer. So not just guessing, but you have to prove why that guess is also true. So here, this is a very frustrating example from the final round of a primary school Olympiad, which I only know the solution of many years afterwards. So this is an isosceles triangle with AC equals to BC and BAC. This angle is 80 degrees. So you kind of know angle C is like 20 degrees as well. And there's this very weird condition that AB equals CD. Two completely in different locations, kind of lengths, AB and CD. And suddenly they want you to find the angle BDC. So it's quite weird. If you just do some standard kind of angle, computing angles via some basic operations like sum of angles in triangle 180, you do 180, blah blah blah. You cannot get that angle. You have to somehow use the fact that AB equals CD to get your answer. And that's the hard part of this problem. And it makes sense because if I don't allow AB equals CD, D could be anywhere on that side, right? So AB equals CD is a crucial point for this problem. So what you can do is to use some trigonometry, to use a bit of sine rule. So let's hope that sine rule can help us solve that problem. Okay, that's just some heavy notation there. So I will draw out some stuff again. So this is the triangle. So here equals here. This is 80. This is 20. Let's use a different color to show D. So you want to use the fact that CD equals AB. I mean, you can just let them be equal to 1, but it doesn't matter. You want to find angles only, you can just scale the triangle however large you want. So you can just let's say AB is 1, CD is 1. Then what do you want to find again? BDC, right? So let's say this is theta. I mean, I like acute angles more, so I'll just let this be theta. You want to find BDC, if I get theta, I can just do 180 minus theta, right? So this is theta. I can write every other angle in terms of theta. Like this would be 20 minus theta. This would be 60 plus theta. Okay, then I can do a bit of sine rule over here because I can do sine rule on the triangle BDC. Well, first of all, this is 1. This one over here should be easily doable by some sine calculations, which is probably 1 over 2 cos 80, is it? You just split the isosceles triangle into half. But anyway, the point is that you can write that in terms of theta, or in fact, in terms of angles only. So now you know this side is CD, is 1. This side is also known. You have angles here. You can do a sine rule kind of equation, right? And solve for theta. So what I can do here is that this is 180 minus theta. It's getting messy here, sorry. So sine 180 minus theta over DC, which is this, equals sine 20 minus theta over 1. Right? So I wrote that thing into an equation in terms of theta. And that's great because now you have an equation of theta, you should expect that you can solve for theta and then the answer would appear. Right? However, if you play around with this equation, it's quite hard to solve what exactly sine theta is. You will solve a lot of quadratic equations and so on. So the point is, you wrote out a sine equation, a sine rule equation, but it's quite hard to solve for theta. So in fact, you just have to look at these two lines. The then sine rule gives, then there's 4 chunks of things over there, right? The left side is sine theta minus 20 over sine 20, and the right side is sine theta over sine 20. So the point is, you want to solve this. You rearrange the equation, you get the second line, cos 20 minus cos theta sine 20 equals sine 20 over sine 80. But you don't know those terms. Those are very complicated numbers. Sine 20, sine 80, cos 20. If you have a calculator, then sure, you can find theta, but you can't use a calculator, and in fact, calculators give you an approximate value only. You cannot be sure that it's exactly equal to some number. So, what can we do? If you rearrange that cot theta, bring some terms here and there, you get a very complicated expression which is also quite hard to simplify. But however, you know that this equation has only exactly one value for cot theta, right? Everything else are constants. So cotangent theta is unique. That means that there can only be one answer for theta, at least for this equation. Alright? You don't know what theta is, but first of all, we know that there's only one possible solution for theta here. Okay. Does that make sense? Then, here is where I guess an answer. And I mean, to guess an answer, you can try a lot of things. You can draw a scaled diagram and see, measure yourself what this thing approximately is, and you see, okay, it's kind of like 30 degrees. Let's just guess it's 30 degrees. And then we just plug it in and see whether 30 works. And 30 in fact works, as we can see. If we plug it in and you rearrange the equation, it becomes a double angle formula for sine 20. So that's quite nice, right? That means if theta equals 30 works, and there's only one possible theta anyway, that means this equation must solve for you theta equals 30, right? So guessing an answer is fine as long as you prove why that answer is unique, or at least prove why your guess is valid. So here's what I did here. And you can get 30 degrees. Of course, I wrote the answer first. Again, it's a good practice to write the answer first. It just makes your solution look nicer. Okay, any questions for this proof? So if you do some calculator on the cotangent theta expression, you can get theta equals 30 degrees. But that's proved by calculator, which is not really what we want. In fact, the calculator might even give you 29.99999. Again, it doesn't kind of help. Any questions here for this problem? Anything that requires explaining? Okay, no problems. Let's just think about this problem. This is a primary Olympiad problem, right? That is at that stage they don't really know sine rule and cosine rule and everything. But again, if a primary school student were to write such a solution, they will accept it because it's a valid proof, it's a mathematically true proof, they will still accept it. But the fact that it's a primary school Olympiad problem means there must be some solution that doesn't require any high school maths. And there is, which is this. But the point is that it's very hard to think of. So here, the first step they do is already something very weird. You erect the equilateral triangle CDC prime, which is a very random thing to do, right? But for some reason, that can kind of help you find out some congruent triangles, similar triangles, and then you can find out it's 30. But it's in the final round of a Olympiad, so it makes sense to be that hard. But yeah, there will be people who give non-high school solutions. Those are very extraordinary students. So this is also a valid solution. Okay, okay. So let's move on. Another technique is to, I mean, this is more like a writing technique, is to kind of write in claims. And let's see what I mean by that. So this one is 2021 Muda. It's a functional equation. I'll explain what that means later. It's just basically a problem on functions. So here, fx is a function defined on the set of real numbers. That means it only takes real numbers as inputs, satisfying f1 equals 2. And for any real number x, these two statements are true. It's quite vague here. I mean, the n in the middle of those two inequalities is not like fx plus 7 and fx plus 1. It's more like inequality 1 and inequality 2, just in case you read that wrongly. So they define, okay, if gx is fx plus 7 minus x, find this value. Okay, first of all, they want you to find g 2021. I mean, if you know f 2021, that's sufficient already, right? So let's not complicate the problem by introducing a g. The problem here, the main problem here is to find f 2021, right? So you want to play around with this two inequalities, because that's the only two information you have, right? And also f1 equals 2. But these two inequalities are the ones that involve all real numbers x, so you can play around with them. And in fact, can anyone think of a way to combine these two inequalities together to force some kind of equality? There's a 7 here, which is quite weird. Like if the 7 were a 1, then those two things must be equal, right? Because it's like fx plus 1 more than equal to fx plus 1, and also fx plus 1 is less than or equal to fx plus 1. So if they were 1, then sure, they are equal. But there is a 7 over there. But in fact, what we can do is this. Fx plus 1 is less than or equal to, yeah, so fx plus 1. But this also means that fx plus 2 is less than or equal to fx plus 1 plus 1, right? I just changed x to x plus 1. Those are still real numbers, so we are fine. Is that okay? But this thing, by this, is less than or equal to fx plus 1, so it's plus 2. So it seems like we can just change 1 to 2. And then we can change 2 to 3, 3 to 4, 4 to 5. Finally, we approach at 7. When we approach 7, then we can force the two of them to be equal, right? So, in fact, I can say even more than that. So, let's say I go back here. I can write in just one full line. I don't have to write so many lines. I can write fx plus 7 less than or equal to fx plus 6 plus 1 less than or equal to fx plus 5 plus 2, and so on, until fx plus 7. And then you say this is by the other inequality, this is less than or equal to fx plus 7. So there's one here, one here. That means everything in between must be squeezed to be that value. Right? Everything here must all be equal. All be equal to fx plus 7. Right? So that's a nice thing. Because I cannot just say fx plus 7. It's quite hard to say. F brackets x plus 7 is equal to f brackets x close bracket plus 7. I can also say that these two terms, the first term and the second term, are equal, which means fx plus 1 equals fx plus 1. I mean, it's technically plus 6 and then plus 7 here, but you can cancel the 6 and 7, right? So I can just play around with the inequalities. I force an inequality out here, because in the end we want an equality, right? We want to find exactly what F2021 is. So we have to force some kind of equality. And we get this. This is nice because if we know this expression and we know F1 equals 2, we know what F2 is, we know what F3 is, we know what F4 is, and so on. So we can find what F2021 is. Right? There's a lot of steps here. I can write it in the neat fashion by doing like that. You can write a chunk of text that kind of focuses on one particular claim, which is not what the question wants, but you can write your own statement in your proof. That's what we call writing a claim, or writing a lemma, or writing a conjecture. So I can write, well, this is just for making your proof look nicer, technically speaking, but it's also nice for your thinking process as well, because you know what the important points are, the important steps are to approach your proof. So the first thing to prove that this thing is true, fx plus 1 equals fx plus 1 for all real x. Then you give a proof. So you know that claim. So it's a nice way of writing what your main points of your proof is. And this means f1 equals 2 implies f2 equals 3 and so on. So f2021 is f2022. And then you get your answer. Is that okay? Any questions about this? There's another proof. No problems? No questions? Okay, a third technique, we kind of saw this technique in the few previous examples that we saw, is to use generalized stuff. We don't want to write particular stuff, we want to try to generalize things. So for example, this Muda question here, very weird sum, right? Very weird sum. So in fact, like you want to cut, let's say the 100th term, it's quite hard to see what that 100th term is. So like even every term here is quite hard to see what it is. How to even find the whole sum from 1 to 2 in 2017. So in this case, you want to try to say, okay, I want to write every term using one line. So just look at the pattern. The pattern is it's a square root. Underneath the square root is a 1 and then a plus 1 over some number squared plus 1 over some next number squared. So we write that in form of k and k plus 1. Because once we write that, we can hopefully find some simplifications. And sometimes when you write in terms of k or in terms of some generalized form, it's easier to see how you simplify them. And in this case, okay, the first step is just you make them have a common denominator, simplify the fraction. It's just fraction stuff for the first step. And the next step is where you can actually factorize it. I mean, the factorizing it is quite expected already because you have a square root outside, right? So, but the point is, the thing on top, you can try all sorts of ways to factorize it. Basically, you want to force it to be a square. And in fact, you can also check that k squared plus k plus 1 squared is the whole k to the power of 4 plus blah 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 stuff. So the point is now I can take away the square root. Of course, I have to ensure that the terms inside is positive. I'm going to take a positive root. So it's k squared plus k plus 1 over k times k plus 1, which I can simplify to the second to last expression. But the second to last expression is quite a familiar problem, right? 1 over k times k plus 1. So the 1 gives you the 2016. The other term gives you a sum of 2016 over 2017. Is that okay? So use generalized things. Generalize things into nice expressions. This one is quite a hard one. So this one is 2019, too long. I mean, it's quite hard because it will be quite intertwined, a lot of variables. But let's see this. So we call a sequence of 5 numbers a good sequence if it's an AP that contains 20 and 19. So these 5 number sequences are what they call good sequences. So for each good sequence, you take the sum of all the numbers. So like the first there would be 100, right? 18 plus 19 plus 20 plus 21 plus 20, 20, 22. And then there's the one below, not sure whether it's going to add up itself. So we add for every sequence a total sum. And we consider all the good sequences and we add all those sums up. What do you get in the end? This is the last question of 2019 so long, I think. So a lot of things are happening here. 20 and 19 could be anywhere in the 5-number sequence, right? It could be anywhere. 20 could be the first one, 19 could be the last one, 20 could be the first one, 19 could be the third one, and so on. There's too many variables involved, too many cases. But one thing we know for sure is that once you know where 20 and where 19 is, the other 3 numbers will follow uniquely, right? Right? You just fix 20 and 19, you want to make it an AP. Every other term is fixed already. Like in the first example, if I tell you that the second term is 19, the third term is 20, then the 18, 21, 22 should be deducible. Right? So what we do is we try to make, we cannot write every single case. There's too many cases in fact. Like 20 could be 5 locations, 19 4. So there's 20 cases. If you want to list out one by one, that's quite tedious. So let's not do that. We're gonna okay. So we're gonna say, let's say 19 is in the ith position, 20 is in the jth position, where ij is a subset of 1 to 5. So maybe I is 5, j is 4, or maybe I is 4, j is 5, I is 3, j is 5. So all those pairs, right? Well, now that I've written the entire case in terms of I and j, I just work in I and j. So assuming ai, I mean the ith term is 19, the j term is 20. So it's the same thing as saying, like, let's say the first term is 19, the second term is 20. So what the other terms are? Another thing, for an AP, right? If you want to add those 5 numbers together, what's it the same as? Is there a quicker way instead of literally adding 5 numbers? If I want to add them all up. For example, the first one. How did I know it's 100 so quickly? If it's an AP, it should be the, but it should be the middle one times 5, right? Because the first one and the fifth one will cancel to become the average of the middle one. The second one and the second to last one will average out to be the middle one. So you can just treat everything as 20. Just treat everything as the middle number. So what you want to do is to find the middle numbers times 5, add all possible middle numbers. Right? So that's our plan. Of course, so now, well, it's 5 times the middle number. The point is you want to find the sum of the middle numbers. Right? So if we start off with I and j, 19 in the I position, 20 in the j position, we can work in terms of I and j exclusively. So like the common difference, first of all, is 20 minus 19 over j minus I, right? Because you have j minus I terms in between, and the total difference is 20 minus 19. And then you know A1, the first term, is you use your AP formulas in high school. Try to find A3 in terms of j minus I. So I know those are not very particular numbers, but if you work in j minus I and you know your algebra, you know what to do, what not to do, like cannot divide by 0 and all those things, you can simplify it to A3 being equal to that one, 19 plus I minus 3 over j minus I. That means for every single case described by I and j, A3 will be this thing. Like if I ask you I equals 5, j equals 3, you can just plug that into that final equation and find out what A3 is. That's why writing in generalized forms are so useful. Does that make sense? So now we want to sum up this last equation over here, this last expression over here, over all possible I and j's. So it remains to find this sum at the bottom. Any questions so far? Okay, so this sum is also quite a hard sum. I mean the 19 part is fine because it's just 19, 19, 19, 19, 19 times the number of ij. That one's fine, but the second term is quite difficult. And okay, so let's see how we can do it. The 19 part is just 19 times 5 times 4, right? Because there is just that many ij's possible. So remember ij here is like this. I sum up over all of these possibilities, I, j subset of 1, 2, 3, 4, 5. And then I got lazy and I don't want to write that again, so I just put ij. So technically I have to write the whole thing, but if the context is there, you can just simplify it to just ij. So the first term is 380. Any questions about that? So why is it 5 times 4? Because there's 5 possibilities for I and then 4 possibilities for j, right? For every choice of I. Now, the second term is where we do something called Gaussian pairing. So, but no, it sounds complicated, but it's something that you already know. It's let's say 1 plus 2 plus 3 until 100. How do you compute that? You take the first one and the last one, right? Second one and the second to last. Third one and the third to last. So that's why we call Gaussian pairing, because the story is that Gauss invented that method, which probably isn't true. So the point here is that we take I minus 3 over j minus I. And okay, since let's say I equals 3, j equals 4 is a case, then I equals 4, j equals 3 is also a case. I just swap I and j, right? So what I can do here is I take the same expression, swap I and j. It's like pairing up the numbers, right? It's kind of like the same thing. So if I do that, if I add up this term in the middle, oh, you can see my mouse, right? Oh, I can just use my mouse to point things. So if you add up these two fractions, this is the plus, this I minus j, you can swap it to become j minus I. The minus 3 and minus 3 will cancel, the I will become I minus j. You will actually just get 1. So, very nice. Two fractions add up to 1. And now you just have to find out what this thing is, which is just 5 times 4. So that sum is also computable. So in the end, you just plug them in. 5 times 380 plus 10. I mean, this here we put times 2, but it's just because I want to pair things up. It's like writing 1 plus 2 plus 3 until 100 the same way but backwards. Just copy the sum twice. Is that okay? Any questions? Okay. Okay, now we come to some exercises. The examples I chose to be harder. This one, I will. It's I cannot say it's easy, but it's fairly easier than the examples. So the first one, you can take out a piece of paper and try. In fact, let's just do it until 17:44 now. Let's do it until 17:50. So 6 minutes. See what progress we can get. I mean, you can just focus on the first one first. Or I should give a longer time. I probably should give a longer time, right? I mean, we just do for 6 minutes. See what anyone can get. I mean, yeah, in the actual OMK, you actually have like 4.3 hours to solve the questions, but we don't have time now, so. If you have any questions regarding the problems, you can also ask me, or anything else you want to ask about the previous things, about in fact anything, you can just ask anyone. You can raise your hand. I will go there and help you. Okay. So the first one, anyone got some pattern from the first few examples? So okay, like for example, if 5 squared plus what was it? Plus 5? Yeah, plus 5. That's 30. So what are the four numbers? 4, 3, 2, 1. Yep. 4 squared, 3 squared, 2 squared, 1 squared. And the next one? Oh wait, so it's 7. Yeah. Yeah. So 5, 4, 3, 2, right? I think. 5, 5, 4, 3, 2. So you probably see a pattern here. Like it should be like 4 consecutive ones. So let's just see what the pattern is. Like in terms of the number that we chose. Like 5, then it gives us 4, 3, 2, 1. Let's just focus on the first number, for example, or maybe the last number. So 5, where we start with 1. 7 is where we start with 2. Can we write a general way? So like n. So it's something to do with n divided by 2 first, right? Because here the numbers are adding by 1, here the numbers are adding by 2. So you kind of like n over 2, which if it's 7, it gives you 3.5. To get 2 with minus 1.5, right? So it's something like n minus 1 over 2. That can we check? Wait, n minus 3 over 2, right? Yeah, so you put in 5, you get 1. You put in 7, you get 2. I mean, you can try the next few ones and then. So the claim now is that we can, let's see if we can prove that n squared plus 5 is just n minus 3 over 2 squared, n minus 1 over 2 squared, because that's the plus 1 of the previous one, and n plus 1 over 2 squared, and n plus 3 over 2 squared. So that's the claim, right? But it's an easy claim because you just expand the right hand side and just see whether it's equal to the left hand side, which it is, I think. Is that okay? So proof, you can just write, well, you can just expand this. Probably know what I mean. So expand, 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 right hand side. The things will cancel, and in the end you'll get n squared plus 5. And of course you can say some other words like n is odd, so those 4 terms in the brackets are integers. Well, it's quite obvious, but sometimes you can stay safe to state the obvious because you never know when they want you to explain something that they want you to explain. Okay, and then if this claim is true, it's automatically proven, right? Because n squared plus 5 is indeed the sum of 4 different squares. So the thing about the problem is that the problem didn't say what the pattern is. Like they just say 4 different perfect squares. But you found out the pattern is that they are consecutive. So sometimes you don't have to look at the whole picture. You can just try and look at some few specific patterns. Okay, and the next question. In fact, I will suggest you to maybe take a picture of it. You can try at home. It uses induction, and the inductive procedure is it's not very lengthy. It's a very short inductive procedure. So you can take a picture of it, and or maybe you can just record the source of it, 2018 Sulong. You can just search it up, and then you can try it out yourself. Okay, a few more examples over here. So, well, we only have half an hour left, so I'll just talk about the first one, and then maybe a little bit of the second one. So the first one is that you have ABC positive reals, distinct one, and you want to prove that this is a real root, right? Well, if you put like positive numbers, it's definitely not 0, right? Because those brackets are all negative, I think. In fact, I said modified here because the original question was random positive reals A, B. In fact, they didn't even say distinct and positive; they just say reals A, B, C. But I think it's easier if you focus just on the positive distinct ones. The other ones you can it's similar. You just have to look at different cases. This one, in fact, you can use a graph to explain why it has a real root. So you can probably look at 1 over x plus a plus 1 over x plus b plus 1 over x plus c, this graph, and then the graph of 3 over x, right? So, you see there's a pen here. It's not highlight. Never mind, I can't draw here. But anyway, the point is to look at the graph of 3 over x, and to look at the graph of x over x plus a, x over 1 over x plus b, 1 over x plus c. And then just prove that they have an intersection, right? Once you draw those two graphs out, you can kind of see why it obviously has an intersection when you draw those 3 graphs out. Okay. I mean, that's one solution. The official solution is to literally expand it into a quadratic equation and then prove the discriminant is non-negative. But that one is quite complicated. And then, okay, the second one over here, you can read it a little bit. So A1, A2, A3, blah 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 is the increasing sequence of all integers that can be expressed as a sum of four distinct positive fourth powers. So here is a bit different. You want to compile all of those numbers that are the sum of four distinct positive four powers. So like 1 to the power of 4, 2 plus 2 to the power of 4, plus 3 to the power of 4, plus 4 to the power of 4. And then all possible ones, put them into this set, rank them from increasing order. And you want to find which ranking is 2018. Well, the thing about this question is it's actually just a trial and error. It's really just a trial and error question because in fact fourth powers are quite large anyway. Fourth powers are quite large anyway, and 2018, when you're talking about fourth powers, is quite small. So the ranking should be quite low. You can start from the beginning and see roughly where the ranking is. So like maybe you can say, okay, consider those numbers where the four numbers over here are less than 7, for example. Maybe the biggest sum is less than 20. Then you can start from there. Anyway, you can take a picture of this and try at home. Or you can just record the source of this. Find it online. Okay. Wait. Okay, now we are trying to let's go specific into the topics. So in Olympiad, there are 4 different topics, or at least that's how the IMO classifies it. So there's algebra, combinatorics, geometry, and number theory. Just now, our examples are kind of like a mix of all 4 of them. So roughly speaking, you can kind of classify every single one of the questions into one of the 4 categories. But there are some problems where there are like crossovers. So you can have combinatorics and even geometry mixed together. So combinatorial geometry. But roughly speaking, you can divide them into these 4 subjects. So one interesting thing to note is that calculus is not required for Olympiad. So, but you are still allowed to use calculus. You are in fact allowed to use any sort of mathematical concepts you want in your solutions. Sometimes knowing calculus can help you to find a better solution, easier solution. Like just now the geometry question, if I use sine and cosine, it's probably easier than you just suddenly put an equilateral triangle on CD. So knowing more is good. It's just that it's not required, and that means if the problem exists, that means the official solution is probably something that doesn't use advanced knowledge. Okay, so we're going to look at algebra. There are quite a few subtopics for algebra. The few interesting ones that I can think of are inequalities, functional equations, recursion, polynomials, and there are many more. In fact, you cannot really group them into subtopics as well. Same thing as how sometimes problems can be crossovers. So let's talk about inequalities today. But I can tell you what these roughly are, just so that you can know what I'm talking. So inequalities, quite self-evident, literally about inequalities. Functional equations, again, we saw one just now. So they give you a properties of a function. So sometimes you want to solve for that function. Sometimes you want to prove a property of that function. So it's all about functions. And recursion is like the Fibonacci sequence. So every term is the sum of the previous 2 terms. That's called recursion. That means it's a sequence where every term is dependent on the few terms before it. That's a whole very large topic. A lot of things we can talk about. But it's not. I don't think I'm talking about that today. Just going to talk about inequalities, I think. And then the 4th is polynomials, which is literally about polynomials. Okay. So inequalities. Inequalities there are a lot of inequalities you can find in Olympiad, but they are all based on one single idea, which is that perfect squares must be non-negative. I mean, real perfect squares must be non-positive, non-negative. And the equality only holds when the number inside the square is 0, right? This basically everything is dependent on this. So we can, even with this concept, we can solve quite a few problems already. Like the first one here, a plus b over 2 is more than or equal to square root ab. In fact, if you rearrange the terms, you can factorize it into brackets square root a minus square root b squared more than or equal to 0. So first example, is that okay? Just like a warm-up kind of thing. So you just rearrange it into a perfect square. And then the second example here is a bit complicated, but you can still base it on the same idea. The x squared plus y squared plus z squared minus xy minus yz minus xz. Apparently you can times 2 and then simplify it into a whole bunch of squares. So yeah, and so using this concept, we can solve quite a few problems. But you can kind of see from the second example how sometimes it can be quite hard to think of how to put them into perfect squares, right? Sometimes you might expect just one whole square, but in fact you have to do like a whole bunch of different squares added together. I'll show you one even worse example. This one over here, this one is right? This one, you start off, you want to prove x plus y plus z over 3 more than or equal to cube root x, y, z. Apparently, you can expand this whole chunk of things, which I had to look it up myself as well because I don't know. But this chunk of things would eventually simplify to x plus y plus z over 3 minus cube root x, y, z. So you can kind of see how these things can grow quite complicated, right? So therefore, there are some well-known inequalities that we can sort of just know or even like memorize, and then use those inequalities in different situations. Like for example, this green example here is actually a specific case of what we call the AMGM inequality. And so the AMGM inequality, first one is that the arithmetic mean. So arithmetic mean is just the usual way we take averages, right? Add them up, divide by the number of stuff. It's always more than or equal to, this thing is what we call the geometric mean, which is kind of like, instead of adding up, you multiply them together. Instead of dividing by n, you take the nth root. So it's kind of like in between as well. It's kind of like an average. It's kind of like a mean. So it's called a geometric mean. But of course, this is just a statement. It's just a theorem. I haven't proved it to you, and I don't think I have time to prove it to you. But it uses a very interesting form of induction, this AMGM inequality. So if we have time tomorrow, maybe I can prove it. So it's I can roughly say that the induction is not about 1, 2, 3, 4, 5, 6 like that, but rather you start by proving the powers of 2 are true. So like 1 to 2, 2 to 4, 4 to 8, 8 to 16. You prove that it's true for n equals to the power of 2. And then you start off, and then you go backwards. So it's like forward backwards induction, but it's a whole new topic. So but the fact that this is a very well-known inequality, so I suggest that you memorize it. And also the equality condition, which sometimes is quite important, is that the equality holds here if and only if all of them are equal. And also make sure that you know that these are positive numbers, a1 to an. Okay, another famous one is the Cauchy-Schwarz inequality, which is, I can just summarize it in this way. So the sum of, so it's basically like a squared plus b squared plus c squared. This whole chunk multiplied by this whole chunk, x squared plus y squared plus z squared, is more than or equal to this sum where I take the pairwise, not the pairwise, sorry, the corresponding, the first one corresponds to the first one, second one corresponds to the second one. I can write to you a specific case of that. So for the two variable case, it will be a squared plus b squared, x squared plus y squared, more than or equal to ax plus by squared. For the three variable case, it will be this. More than or equal to ax plus by plus cz squared. Then you can kind of go to a bunch of variables. So this is called a Cauchy-Schwarz inequality. So these are the two inequalities that it's kind of like a must-know for Olympiad. There are other inequalities. In fact, there are hundreds of other inequalities that you get. There are books where they just talking about inequalities. But knowing these two can already help you solve quite a few problems, and hopefully OMK problems as well. So let's see. So the same problem just now, x squared plus y squared plus z squared more than or equal to xy plus yz plus xz. What we can do is to do a Cauchy inequality thing, which is instead of ABC, I put xyz. Instead of another type of ABC, now I put yzx. Then I take the pairwise, like not pairwise again, the corresponding, the first one with the first one, second one with the second one, third one with the third one. So it becomes xy, yz, and zx. And then you just take the square root. So that's one shorter way that you can prove this inequality. I mean, there are multiple ways to prove this inequality, in fact. Is that okay? Any questions? Okay, so okay, you can take a picture of this. It's an inequality question. It's quite a fun one actually. Now, first of all, let's look at the previous two first. Why AMGM is powerful is because it converts a sum into a product. A sum into a product. Whenever you see a sub case where you want to see, okay, you get to some point where the sum of things, but you want to try and in the next step try to convert it into a product, you can try to use the AMGM inequality. And the powerful thing about Cauchy is that you can convert squares to non-squares. So, like, you can also do something like this. A squared plus B squared, 1 squared plus 1 squared, is more than or equal to A times 1 plus B times 1 squared. So, this is also a very nice inequality. So, you basically convert sum of squares into the whole sum squared. So, Cauchy can help you do these things. So notice this one, a squared plus b squared, and then on the right side is a plus b. That's kind of related to the example problem 1 here, except it's not like a plus b is ax cubed plus bx. So you kind of try and see whether you can put x somewhere into that Cauchy inequality as well. Okay, and for the second one, very direct question. Just want you to prove that this inequality holds. Well, there are a few solutions that you can do for this. One example that I can suggest try is to treat this. I mean, you don't have to use AMGM or Cauchy, but my first instinct of proving this is to see this thing as a quadratic in Z, because it's Z squared, and then treat x and y as constants. Then the whole thing is kind of symmetric in x and y. You can write it in terms of x plus y and x times y. But yeah, we'll keep this on hold. If you have time, you can try them out. So can I change the slide now? Anyone want to like take a picture or? Okay, no one. Right. Okay. Okay. Now combinatorics. Combinatorics is very similar to permutations and combinations. In fact, the word kind of looks like that as well. So combinatorics, I mean, it's my least favorite topic in Olympiad, but it's quite important. So the most prominent questions that you have on Olympiad is combinatorics and geometry. Those are probably normally the hardest. Normally you have, because IMO has 6 questions, normally 2 are combi, normally 2 are geometry. But combinatorics is about combinations and like arranging stuff in ways that can be surprising. So there are a few subtopics here. Again, it's not limited to this. Again, first of all, it's about bijections. That one I can roughly tell you what it is. Bijections are basically you want to count something. You want to count something. You try and count something else that gives you the same answer. Like if this lecture room were to be full of people, I don't have to count one by one how many people there are. I can just ask the guy how many chairs there are here or something. So you just convert a problem into something else that's easier to count. That's what we call like bijections. Of course, that's not the official definition of bijection, but something like that. So the second one is a pigeonhole principle, which is what I'm going to talk about today. Because it's one of those things where the concept itself is easy, but to apply it is incredibly difficult. So, and then we have combinatorial sums. These are sums about the choose function, like n choose 1, the nc one. I like to call c as choose because literally it's like n objects choose k objects. So like n choose 1 plus n choose 2 plus n choose 3. These kind of sums. In fact, it's kind of like algebra kind of combinatorics. And then graph theory is also quite interesting. Graph theory is about networks. It's about nodes and vertices. So like You can connect one dot to the other and one to the other. If you have heard of the Königsberg 7 bridges problem, that's the birthplace of, that's the starting of graph theory. And then a few more examples. So let's look at pigeonhole principle. If we have, I should have said pigeonhole instead of boxes, but so 100 pigeons are distributed in 99 boxes is a bit cruel, but I mean the namesake itself is from pigeonholes. So let's say 100 pigeons is distributed in 99 pigeonholes. What can you say about the number of pigeons in each pigeonhole? 99 pigeonholes only, but in total you have 100 of them. What can you say? There must be one pigeonhole with more than one, right? Because if you want to fill in every single pigeonhole with at most one, you only have at most 99 pigeons in total. So that's basically pigeonhole principle. If you have n plus 1 objects distributed in n boxes, there must be one box with at least 2 objects. Very intuitive, right? Okay. Now, there's a generalized form. For example, if I have 100 boxes, right? If I have 100 boxes and I put 101 objects, okay, at least one box has 2 objects. But if I put 201 objects, then I can at least guarantee one box with at least 3, right? So generalizing, you can kind of say this: if capital N objects is distributed in, sorry, that should be M, not N. Yeah, so M for monopoly, M boxes. There must be one box with at least this number of objects. So how do you read this? This is what we call a ceiling function. Basically, you divide the number, like 7 divided by 4, or maybe like here, 100 divided by 99, and then you take the integer that is at least above it. So that's what I call a ceiling. So if you get 6.5, that means it's 7. If you get 6.1, it's also 7. If you get 6.9, it's also 7. If you get 7, it's also 7. So that means you round up. You round up. I mean, like, not the usual way we say round up, but literally upwards, round upwards. And then there's something called floor function, which you round downwards. Okay, any question about that? And then the third one is the most obvious one. If an infinite number of objects is distributed in n boxes, there must be at least one box with an infinite number of objects. Right? I mean, technically the first one is the most obvious one. Yeah. These are the 3 forms of pigeonhole principle. But let's see what we can do about them. Now, so here, I kind of put the answer same as okay. Never mind, put it in the same slide. At most, how many elements can you take from the set 1 to 1000? So that no 2 elements add up to 1000. So you can plug elements from 1 to 1000, like just extract it. But at most, how many can you do? Like maybe you got unlucky and the first one you get is 1, the next one you get is like 999 already. Then for 2 elements you already get 2 elements that sum up to 1000. But if you're the most lucky case, at most how many can you get? So here, what we can do is to use pigeonhole principle by doing the following operation: is to group 2 numbers that add up to 1000, like 1 and 999, 2 and 998, 3 and 997, so on until 499 and 501, and then I just throw 500 and 1000 in some other box. Now, if we have these boxes, then using pigeonhole principle, I can say that you cannot take 502 elements, right? Because if you take 502 elements, well, just pigeonhole principle, 2 of them must be in the same box, and then you get 2 numbers that add up to 1000. Does that make sense? But of course, that doesn't guarantee us that 501 works. Again, if you want to prove like 501 is the maximum, you have to prove that 502 cannot, and then prove that 501 can. But proving that 501 can is just a construction problem. You can just try out and just make sure you get like the first numbers here, like maybe 1, 2, 3, 4, 5, like that. And I think that works, right? Like 1 to 500, and then you just put 1000. Yeah, so 501 works. So the pigeonhole principle tells you that 502 doesn't work, but then the 501 works. You have to, because sometimes pigeonhole principle tells you that this doesn't work, and apparently 501 also doesn't work. Then you have to do more work about that. Okay, any questions about this problem? No, okay. So here, so 2 very classic problems. I'm not sure where they came from because I just find it out by memory. So what is the maximum number of elements you could pick for 1 to 2024? So it can be just n. I just put 2024 here because next year is 2024. So that no two distinct elements A, B are picked with A dividing B. So you cannot pick like 1 and 2. You cannot pick like 6 and 12. You cannot pick like 5 and 10. You cannot pick like 5 and 15. So using this, how many can we plug? So this one, so pigeonhole principle is an easy concept, but the part where you have to design your own pigeonholes is quite hard. So you have to make sure that you design a collection of sets where you can apply pigeonhole on. So how do you partition 1 to 2024 into a whole bunch of boxes such that if two of them are in the same box, kind of guarantee that they are one divides the other. So any way we can try that? Let's just try this problem today. Like maybe I can put 1 and 2 in the same box, right? I can put 1 and 2 in the same box. So you put 1 and 2 in the same box, that means 3 cannot be in the same box anymore, right? Because picking 2 and 3 is not what we want. We want to design the boxes so that if two of them are in the same box, they satisfy what the question doesn't want, which is divide each other. So 2 and 3 cannot be there anymore, but 4 can, right? Because 1 divides 4, 2 divides 4, and 1 divides 2. And you can kind of go on. The next possible one can only be 8, right? So let's move on until the largest power of 2 that doesn't exceed 24, which is 1024, right? The next one is 2048. So that I can put as one box, right? And then okay, how about some other sets? So let's start with the one that isn't written. So let's say 3. So 3 is the first one that isn't written. So if 3 is there, can we do like something else? Like the same thing where we design a box where if we have 2 in the same box, 1 divides the other. Well, the first one is about multiplying 2, multiplying 2, multiplying 2. The second one, I can also try multiplying 2, multiplying 2, multiplying 2. 12, 24, blah blah blah, and then like the largest multiple of the largest 3 times 2k kind of number that is lower than 2024. I'm lazy, I'm not going to find that, but you get what I mean probably. So you just multiply by 2, multiply by 2. So that's the second box. And then the third box, what does it start with? What's the lowest one that hasn't been chosen yet? 5, yeah. So in fact, well, you can kind of see one thing. The first numbers over here should be just all the odd numbers, right? And so let's see if that conjecture actually holds. So again, this is about guessing a result. So we just start with every odd number and then just keep multiplying by 2 to design our boxes. Okay, first of all, there is no overlaps. Why? It's actually just, you can think of it in terms of prime factorization. So even in prime factorize, you have a power of 2 and you have a unique odd part, right? So you think of it in that kind of way, you can kind of make sure that there's no element in the same box over here. Because the first box is everything with odd part 1, the second box is everything with odd part 3, the third box is everything with odd part 5, and so on. So this is our boxes. How many boxes are there? Until 2024, right? That means the last one should be like 2023. And then it just ends there because you cannot multiply by 2. So how many boxes are there? One way you can count such things like 1, 3, 5 until 2023, how many numbers are there? What I do is I like to add numbers to every single element or multiply everything by a single element. Like here I can add 1 to everything and then divide by 2. Then it becomes 1, 2, 3 until 1, 0, 1, 2. Then I immediately know there's 1, 0, 1, 2 boxes. Is that okay? That's the one way that I like to count things. So I just kind of bijack them into something else that's nicer to count. So there's 1, 0, 1, 2 boxes over here. So at least from pigeonhole principle, we know that if 1, 0, 1, 3 objects are chosen, then 2 of them must divide each other, right? So 1, 0, 1, 3 cannot. that make sense? Does that make sense? Of course, 1012, it doesn't guarantee that 1012 cannot. So anyone wants to try and see if you can find an example of 101, 1012 elements. So first of all, it must all come from the same, they must all come from each box, right? They must all come from each box. Choosing all the odd numbers doesn't work, right? Because, for example, 3 divides 9. So you cannot just choose the odd numbers. So you have to think more carefully about this, how to design 1012, or maybe even 1012 doesn't work. So, but in fact, it does work. And what we do is to choose, here is 1 to 2024, right? The answer is, to choose 1012, I just pick 2024, 2023, 2022, dot dot dot, then 101, what's the 1012 element? 1013, right? This is a 1012 set where none of them divide each other. Because the only way you can divide each other is to divide by 2, right? I mean, at least multiply by 2. But 1013 multiplied by 2 is already exceeding 2024. So the answer is that 1012. 1012 is the maximum number of elements where you can choose, so that no two of them divide each other. Okay, and the next one is also quite an interesting one, but this is more like a number theory kind of plus combinatorics kind of question. So you want to prove that there's a power of A. So A is anything. Like A is not what you choose. A is just given to you. A is a fixed positive integer. You want to prove that there is some power of A that ends with an arbitrarily large amount of zeros and then a 1 at the end. So that means you can find a power of A that ends with 0, 0, 0, 0, 0, 0, 0, 0, 1. I don't know how many zeros I said there, but it's still possible to find such a power of A. And if you want to convert that into number theory problem, if you know modular arithmetic, that is equivalent to saying it's equal to 1 mod 10 to the power of n. So you can start off with that if you we're running out of time, so you have 7 minutes left. So again, that's something we can try at home. Okay, so here are the actual OMK problems that I found. So in 2019, there are actually 2 of them. The first one is a section A problem. So I'm not sure if you know, OMK has 2 sections, section A and section B. Section A is the part where you just have to write answers. There's a box there for you to write your answer, so normally it's a simple answer that you can fit in the box. And section B is where you write solutions, except that autobiographical number thing where I can just write a single line. But yeah, the section B is where you have to explain your progress, or at least your proof. So okay, so the first one here is from section A, the second one here is from section B. A group of students collected 200 seashells at the beach. What would be the maximum possible number of students in the group if every student collected at least 1 seashell and everyone collected different numbers? I think this was the first question of the test. The first question of the test. So in total there are 200, right? You want to maximize the number of students, but everyone must have a different number of seashells. So what's like the most extreme possible way? Everyone has the least amount of seashells, right? There's one person with exactly 1, there's one person with exactly 2, there's one person with exactly 3, so on. So you just kind of see like 1 plus 2 plus 3 plus 4 until what kind of threshold where you can not exceed 200. So that will be your extreme number. Yeah, okay. And then the second one is, oh yeah, so the second one is another pigeonhole problem. Wait, no. Second one is also a section A problem, apparently. So there's this set A, 1 to 100, and Fk, so positive integer k, represents the maximum size so that no 2 elements in the subset differ by k. So it's kind of like the pigeonhole the pigeonhole principle problems that we said before. It's kind of like a procedure where you pick stuff from a box, from a large box. You don't want some of them to have some property. So here the property is you don't want them to differ by k. So for example, f1, so that's k equals 1. What would f1 be? So how many numbers can you pick from this 1 to 100 so that no two of them differ by 1? Then the simplest case I can think of is 1, 3, 5, 7, 9, and so on, right? And that would mean f1 is like 50. Of course, you have to prove that it's 50 really. But here, determine the number of possible values of k that fulfill the condition fk equals 50. We have 4 minutes left. Let's just try. Let's just try the first one. In fact, that's probably doable in 4 minutes. So the first one is 200, right? We want total to be 200, but every single term is positive and different. So the extreme case is 1 plus 2 plus 3 until some kind of number, and you want this number to be at most 200. If it's more than 200, that means impossible. If it's like 1,000 people, you definitely know it cannot be 200 seashells in total if everyone's number of seashells is different, right? So you want the cutoff point where it's less than or equal to 200. So n plus 1 less than or equal to 400. And here is where we can exercise some estimation. So 400 is about 20. 400 is exactly 20 squared, right? So we know that n equals 20 doesn't work because that's 20 times 21. And n equals 19 actually works. So n is at most 19. So you don't have to really do the quadratic and solve a very complicated quadratic inequality. Sometimes you can just estimate. So here it's like n less than or equal to 19. That means you can have only at most 19 people. If there were 20 students, the total number of seashells would be at least 1 plus 2 plus 3 until 20, which exceeds 200. Right? So by this we prove that 20 doesn't work. But why does 19 work? So why does 19 work? If I do 1 plus 2 plus 3 plus blah 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 plus 18 plus 18, 19. This would be 19 times 20 over 2, so that's 190. Okay, so but that's not 200. How do we make it 200? But everyone is different, right? Everyone's seashell is different. You just want to try and somehow make it into 200 to make sure, just explain why 19 works. Yeah. Let's take a random person and just take more seashells, right? Let's say I just take the last one over here. Since you need like 10 more to get 200, this is let the last guy to have 29. Then it adds up to 200 already. So 19 indeed works. So there is a case where there are 19 students. So that means the answer is 19. Because we proved that 20 doesn't work and 19 actually works. That's how you prove something is a maximum. It's what we call an optimization problem. Normally there are two parts. You first prove why it works, and then you prove why the other case doesn't work. Is that okay? Any questions so far? And that's basically my whole thing for today. Tomorrow there's more, but yeah. So that's all for today. Any questions you wanna ask before we end? Okay, don't worry. Okay, if you want, you can also come out and ask me. Okay. Thank you.